So now we will look at continuous linear functionals on LP of mu. So recall that we did characterize continuous linear functionals on L2 of mu. Since we had an inner product there, we got a characterization saying that any continuous linear functional on L2 was given by an inner product. We will do something very similar for LP, except that the continuous linear functionals on LP will be characterized by functions in LQ, where Q is the conjugate exponent of P. There are some restrictions like mu has to be sigma finite and P has to be strictly less than infinity, etc., which will be clear when we write down. But before we get into the exact statement, we will look at continuous linear functionals and just prove some elementary general result, which because each time we have something like that, I do not want to keep proving it. So let us just write down some results which will prove and will be used again and again. Okay, let us start. So we have a space X F mu. We will assume that mu is a positive measure. Mu is a positive measure. Right now we do not need to assume that it is sigma finite, it is only a positive measure. So we look at 1 less than equal to p less than equal to infinity and q conjugate exponent of p, okay, conjugate exponent of p. So what was that? 1 by p plus 1 by q equal to 1. And we of course have the LP space, right, LP mu, which is complete. We proved that it is a complete normed space, right. So there is an LP norm and the LP norm gave a metric and it is a complete metric space. Now let us fix G in LQ, okay. So P is fixed and we are looking at G in LQ, a fixed function. Define T. So this is going to be our linear functional LP of mu to C by T of F. So if I take an F in LP, I should tell you what is T of F is. This is equal to integral over X F G d mu, okay. Well, we have to see that it is finite, it is well defined and things like that. So for that, look at modulus of Tf just to see that it is finite. This is of course less than or equal to integral over x mod f mod g d mu, which of course is less than or equal to by Holder's inequality. Remember, G is in LQ and F is in LP, right. So F is coming from LP and they are conjugate exponents. So Holder's inequality will tell me that this is mod f to the p d mu 1 by p integral over x mod g to the q d mu to the 1 by q, right. This is just Holder's inequality. Holder's inequality. Okay. And this is the LP norms, right. So let me write this as LP norm of F and LQ norm of G. So T is well defined and it is a finite complex number for all F in LP. Now note that suppose I want to say T is continuous, okay. So suppose Fn converges to F in LP, okay. Well, what happens to Tfn minus Tf? I want to say Tfn converges to Tf in the complex plane, which is same as saying Tfn minus Tf goes to 0, right. So I will take the modulus. So this is equal to, T is linear, so T of Fn minus F, right, which by this computation, so instead of F I have Fn minus F there. So I will have this is less than or equal to Fn minus F LP norm, right, that is the first term, times the LQ norm of G. But Fn goes to F in LP and so this will go to 0, right, this goes to 0, which means that Tfn converges to Tf and so T is continuous, and so T is continuous. So any inequality like this gives me that T is continuous, okay. So not just that, we have a little bit more, so let's complete that part. also we have, so it's continuous, and we have the extra equality, so that is supremum over LP norm of f less than or equal to 1. So that is the unit ball in LP, and I am taking the supremum of T on the unit ball. This is actually equal to the LQ norm of G. So T is defined by G, and I am saying this quantity on the left hand side, that supremum of LP norm of f less than or equal to 1 T mod Tf is actually equal to the LQ norm of G. Okay, so let us see why. So simply take f to be, so maybe I will write it down here. This is easy. Take f to be mod G to the Q, okay, divided by G. Of course, to divide by G, G should be non-zero. So you take wherever G not 0, you take that function, and 0 otherwise. Okay. So this is of course a measurable function because G is measurable, and so this would be a measurable function. And I want to say it is in LP, right. So claim is that f is in LP. F is in LP. Remember P and Q, P and Q are fixed, P and Q are conjugate exponents. Okay. How do I say something is in LP? It's a measurable function. So I look at the modulus of that and take the pth norm, right, pth power, and see what happens to this. If this is finite, then f will be in LP. Well, let us see what is the integral. So this is equal to mod f to the p. What is mod f to the p? So mod f is, for all practical purposes, mod f is mod g to the q minus 1, right, and it's 0 when g is 0. So that part we will not bother about because that will give 0 anyway. So and when I take the power p, so mod f to the p would be the power of this to p, which is p into q minus 1. So mod g to the p into q minus 1, okay, d mu. Okay. But what is p into q minus 1? So p and q are conjugate exponents. So 1 by p plus 1 by q is equal to 1. Okay. So 1 by p equal to 1 minus 1 by q equal to q minus 1 by q. So cross multiply, you will get q equal to p into q minus 1, right. So p into q minus 1 is q. So this is integral over x mod g to the q d mu, which I know is finite because g is coming from LQ. So f is in LP. So I can calculate Tf, right. So let's compute T sub f, T of f. So T of, well, not f, I should perhaps normalize it. So instead of simply f, so you look at f, so f is an LP, divide that by the LP norm of f. Okay. So this would be an element in the unit ball, right. Any vector, if you divide by its norm, it comes to the unit ball, and you look at T of that. Okay. So this would be equal to, well, 1 by norm f to the p, because norm f to the LP norm of f is a positive number, right, and t is linear, so that comes out T of f. Well, T of f is defined to be integral against g. So 1 by LP norm of f integral over x, Tf is f times g d mu, right, that is how it is defined. But we have chosen f, right. So you plug that in, you will see that g gets cancelled wherever g is non-zero. Wherever g is 0, the integral is 0 anyway. So if g gets cancelled, you will simply get mod g to the q, right. So this is 1 by norm f, right, integral over g. Fg is just mod g to the q, right, d mu. Okay. All right. So we are in good shape now. So this is equal to, let us see, this is equal to, so I can write this as g LQ norm of q divided by LP norm of, right. Okay. But what is the LP norm of f? Well, we computed this. So the LP norm of f is given by the pth root of this quantity. Okay, so pth root of this quantity. Okay, so this is equal to g q q by LP norm of that would be, you look at LQ norm of g. Okay, so maybe I should write it down. So I am looking at LP norm of f. This is equal to integral over x mod g to the q d mu, right. So I just use this, fine, to the p, sorry, to the 1 by p, right, because here I should take a power 1 by p to get the LP norm, which I write as okay, so I should write this as, I want to put a q and a power q. Okay, so that bringing in LQ norm of g, right. So I can write this as, so I multiply this 1 by q and then q. Okay, so I have not done anything. Q and q gets cancelled. Okay, but if I look at this and this separately and I have a 1 by q, I will get LQ norm of g, right. So that is LQ norm of g, and I have a q by p, correct. Okay, so this is, so this quantity is just this, so that is q by p, okay, which is equal to the same quantity by q to the q and same quantity to the q by p. So that is LQ norm of g q minus q by p. Q minus q by p is, well, it is 1, right, because q minus q by p is q into 1 minus 1 by p, but 1 minus 1 by p is 1 by q, so that is q into 1 by q, that is 1. Okay, so this is simply LQ norm of g. So at this unit vector I will get the LQ norm of g, and so this would be equal, right, because from here we know it is less than or equal to, from the inequality here we know that. So let us, okay, maybe I should write it separately. So the first thing we proved was modulus of TF is less than or equal to LP norm of f into LQ norm of g, right. This was the Holder's inequality. So this immediately implies that if I take the supremum of T over the unit ball, modulus of TF, that is of course less than or equal to, so if these guys are less than or equal to 1, I will simply get this. Okay. Now taking f to be equal to mod g to the q by g when g is not 0 and 0 otherwise, we proved that for this particular f, so let us call that f naught, we proved that T of f naught divided by the LP norm of f naught. So this would be an element in the unit ball, right. So f naught divided by LP norm of f naught is in the unit ball. Okay. So T at that point is actually equal to the LQ norm of g, right. That is what we just computed, right. We got this. So the supremum will be attained, right. So this tells me that supremum of LP norm of f less than or equal to 1 modulus of TF, this is equal to LQ norm of g. Okay. So whenever T is defined to be TF equal to integral over x f g d mu, right. In case of L2 we write it as an inner product, you can put a g bar if you want, but it gives you the same. So this is for f in LP, okay, and g in LQ. So this is for every f in, and g is fixed in, so g is fixed in LQ, and you define this linear functional TF, then you have this, it is continuous and you have this equality. So this is what we aim to prove. We will prove the converse. If I start with a T which is continuous, I am going to get this. But before that we look at some general statements about continuous linear functionals. Okay, so let us start that as separate. So I have LP mu, I can look at, well, I will leave out the infinity for the time being. We will not characterize continuous linear functionals on L infinity. Suppose T is from LP mu to C linear, okay, then the following are equivalent. So I should write this as a theorem. So then the following are equivalent. Okay, so write it as a theorem if you like. A T is continuous at 0. So remember, this is a vector space, so there is a 0 which is a 0 function or the equivalence class corresponding to 0. T is continuous at 0. T is assumed to be linear. Okay. Then T is continuous, right? T is a map from LP mu to C. It is continuous at all points, not just at 0. C supremum over the unit ball of T is finite. Okay, so this we define it to be norm of T, norm of the linear functional T. Okay, so that is the notation. Okay, so norm of T is finite. So let's see a quick proof of this. This is a very easy proof, but let's just go through it, because this is something which I can use again and again without proving again and again. Okay, so T is continuous at 0. So I want to prove that if it is continuous at 0, it is continuous everywhere. Okay, so let us see that. So take any, so let Fn converge to F. Fn converge to F where in LP. In LP. Okay, I want to show Tfn converges to Tf, right? So need to show that T of Fn converges to T of F where in the complex plane, right? That is what you mean by T is continuous at F, at the point F. Well, Tfn, so this is where linearity helps. Tfn minus Tf equal to T of Fn minus F, because T is linear. And Fn minus F, what happens to Fn minus F? Fn converges to F in LP. Okay, so Fn minus F converges to 0 in LP. So this is a sequence which converges to 0. So this will converge to T at 0 by continuity at the point 0. T at 0 is 0, of course, right? T is linear, so T at 0 is 0. So that is same as saying Tfn converges to Tf. So if T is continuous, so this is not very surprising, because it's linear. Continuity at 0 will imply continuity at all points. Okay, in general, if you have a group homomorphism on a group with a topology, if it is continuous at identity, it will be continuous at all points. Okay, so let us see how B implies C. So remember, C is given by this quantity norm T, and I want it to be finite if it is continuous. Okay, so suppose not. Suppose not. So what does that mean? That means the supremum over the unit ball of T is infinity, right? That is what it means if it is not finite. So hence, so we choose a sequence which goes to, hence there exists Fn such that the LP norms of Fn are less than or equal to 1. So that means they come from the unit ball, but Tfn goes to infinity, right? So modulus of Tfn goes to infinity in the complex plane, right? So the Fn's are complex numbers. Okay, so consider Fn divided by T of Fn. Remember, T of Fn is a complex number, right? It's a scalar. Okay, what happens to this function? So these are all in LP, right? Because Fn's are in LP. Tfn is a number, you are multiplying Fn by that number. So these are all in LP. Let's look at the LP norm of them. So LP norm of Fn divided by Tfn, right? So what do? You take the pth power and integrate and take the 1 by p, right? Root 1 by pth root. So Tfn is a scalar, so that comes out. So that comes out as modulus of Tfn, right? Alpha comes out as modulus of alpha out of a norm, right? And I have LP norm of Fn's. But LP norms of Fn's are less than or equal to 1, right? So this is less than or equal to 1 by modulus of Tfn. But modulus of Tfn goes to infinity, so this will go to 0. So, Fn by Tfn is a sequence of functions going to 0, right. So, Fn by Tfn, so these are functions going to 0 in LP mu, okay. But it's T is continuous, T is continuous. I am trying to prove that the supremum over the unit ball is finite. T is continuous, so T of Fn by Tfn, right, that is the sequence which goes to 0, should go to 0, T of 0 which is 0, okay. But Tfn by Tfn is, so what is this? This is T of Fn, this is a scalar, right, that comes out. So, T of Fn, and so it is 1, it cannot go to 0, that is a contradiction. So, it is not, so T is not continuous, okay. Alright, so we proved that A implies B, and we proved B implies C, and now we will prove C implies A, okay. That is that's trivial. So, C implies A, C implies A. So, what is C? C says that supremum over LP norm of F modulus of Tf is finite, right. This is what we called norm of T, okay. So, we will keep that notation. So, if I take any F in LP, what do I know? Well, I know that F divided by LP norm of F is in the unit ball, right. So, that would be in the unit ball. So, if I look at T of that, so that is just T acting on some vector in the unit ball, right. Modulus of that I know is less than or equal to norm T, because if I take supremum over all such things in the unit ball, I am getting norm T which is finite, right. This is one such element. So, this is true. This of course implies, because this is a scalar that comes out and goes to the right hand side, okay. So, I will get modulus of Tf, okay. So, I wrote Fn, so let us write F there, F is less than or equal to norm T times norm Fp, right. This is true for every F in LP mu, okay. And that is all is necessary for continuity, right. So, now if I take Fn going to 0 in LP, well, what will happen? Then the LP norm of Fn's also go to 0 in the real numbers, and so the right hand side will go to 0, which means that this goes to 0, right, because of this. So, T is continuous at 0, continuous at 0. So, whenever you have this particular inequality, that is same as saying it is continuous. Okay, so these are general results for continuous linear functionals, okay. Now, our aim is to characterize continuous linear functionals. So, we are going to write this as a theorem. This is a slightly longer proof, but let us write down the complete theorem, okay. Suppose 1 less than to p strictly less than infinity, okay. Mu is a sigma finite measure, okay. Mu sigma finite positive measure, okay, on, so you have x and script f. Let T be a continuous linear functional on LP mu, okay. So, remember p equal to infinity is not included, okay. LP mu be a continuous linear functional. So, when I say functional, it takes values in the field complex plane or real numbers depending on the vector space, okay. So, it is continuous linear functional. Then there exists a unique G in LQ, okay. What is Q? Q is the conjugate exponent, right. So, 1 by P plus 1 by Q equal to 1, such that T is given by that function G. So, Tf is equal to integral over x f times G T mu. This is true for every f in LP. Okay. And whenever you have this integral, you know that another equality is true. So, what do? You look at norm T. This is simply supremum of over the unit ball of modulus of Tf, right. So, whenever we have this integral, we know that it is actually equal to the LQ norm of G. Okay. So, we are identifying the norm of the linear functional as the LQ norm of the function G, which defines the linear functional T. Okay. So, I hope the statement is clear. So, for L2 we have done that. Okay. So, recall that we proved this for L2 of mu without the assumption that it is a sigma finite measure, right. For any L2 mu is a positive measure, we have this characterization that it is given by an inner product, right. So, instead of writing G, we wrote G bar, that is the only difference. But we have proved this for L2 mu without the assumption that mu is sigma finite. Okay. So, we will continue with the proof. Now, proof we have to get a G first, and there is a statement about uniqueness. So, let us get rid of that. Some of these are generally easy. So, we will get rid of that. So, uniqueness. Okay. Suppose there exists G1, G2, okay, in LQ such that TF. So, TF is given by both G1. Okay, so let us write this in the other order. So, TF is given by F G1 d mu, and of course, it is given by G2 as well. So, F G2 d mu, and of course, this will have to be equal for every F in LP, right. G1 and G2 come from LQ, where 1 by P plus 1 by Q equal to 1. So, what do we want? So, uniqueness means what? We want to show. So, need to show that G1 is equal to G2 almost everywhere. Of course, G1 equal to G2 almost everywhere, right. That is what. So, as elements of LQ, they are same. Okay. So, because these two integrals are same, you subtract, you will get that integral over x f times G1 minus G2 d mu is 0 for every f in LP. So, you can take f to be indicator sets, characteristic functions. So, take f to be. So, you will get integral over E G1 minus G2 d mu is 0. So, now you know how to do this, averages are 0, etc. So, this is true for every set in the sigma algebra, right. So, this of course implies G1 minus G2 equal to 0 almost everywhere, right. So, the uniqueness part is easy, that is precisely what the same as G1 equal to G2 almost everywhere. So, uniqueness is done. So, we do not know if the G's exist first of all. If there exists a G which defines T, it is uniqueness. Okay. So, we need to show that. So, all we need to show is, all that remains is, which is the main part of the proof, all that remains is the existence of G, That means, if I take a continuous linear functional T, then there is a G. So, uniqueness we have already proved such that this is true, right. Once this is true, I know this is also true, that we did, right. So, all I have to do is to prove that there is a G which will give me the integral of Tf as the integral of G against F. Okay. So, we will start with the proof. So, first, two steps. First consider first consider mu of x to be finite. In the second step, general case, so remember mu is sigma finite. So if mu is sigma finite, we know that there exists 0 less than w, strictly less than 1, w in L1, right. So we will construct a finite measure from this, finite measure using w. So this we have seen before, and use 1, right, and use 1. So that is what we will do. Okay, so let us stop here. So we have only stated the continuous linear functionals on LP of mu are given by functions in LQ and the equality of the norm. So LQ norm of G is same as the LQ norm, the norm of the continuous linear functional, which is the supremum of the modulus of TF over the unit ball in LP, right. So we have just stated, and we have seen that uniqueness part is trivial. If you have two functions G1 and G2 defining the same linear functional, then the G1 and G2 will have to be equal almost everywhere. So in the next session, we will try to complete the proof of the characterization. We will start with finite measures, prove it there, and then use a trick, so which we have seen before, to prove it for sigma finite measures. Okay, so let us stop here.